talking about the first group called alkali metals. These are group 1 elements. Now, I need to make a kind of a distinction with these elements because the elements in group 1 start with what element? Group 1 starts with hydrogen. But here's the kicker, is that hydrogen is not a metal, right? Hydrogen is a nonmetal. It only sits in that location on the periodic table because of its number of valence electrons. Okay, we're going to talk about valence electrons here in just a minute, but hydrogen sits in there for another purpose. So although it sits in group 1, it is the only one of them that is not an alkali metal. Okay, so I listed off all of the different elements that are part of the alkali metal group. You don't necessarily have to write those all down. What you could do is just say, except hydrogen, right? If you wanted to do that, you could, right? Group 1 is all of alkali metals except for hydrogen. In general, they have like a kind of shiny, silvery appearance. They are really soft metals. And so when I mean soft metals, they almost have the texture of like softened butter. You can kind of cut them with a butter knife. They're not really tough. They're very soft metals. Okay? They are not found in nature as free elements. And so what I mean when I say that is that you will not walk around anywhere, a forest or whatever, and find a hunk of lithium metal sitting there. You just won't, right? You won't find sodium metal or potassium metal just sitting there, okay? And that's because they are super, super reactive. They don't really want to exist by themselves. They want to share their electrons. They want to react with other elements. And so when they do that, they form a compound. So most of the elements in group 1 that we know of and we utilize them as part of a compound. Okay? Can you remind me, what is a chemical compound? What's a compound? Elements that are bonded together. So it's multiple types of elements. Okay? So give me an example of one of the elements in group 1 that is familiar to us. What's one that's familiar to us? Give me a metal that's familiar to us. Potassium is the one I think of most often. Where do we hear or know about potassium? In bananas. It says bananas is a good source of potassium for our bodies, and our bodies need potassium to function correctly. Would we agree with that? Yeah. But do we see chunks of metal, potassium in a banana? No, right? That's because potassium is found in bananas as a part of a chemical compound. And when we ingest that chemical compound, our body does its job to extract the potassium on its own, that ion of potassium, and to use it the way our body needs, right? So same thing with calcium. Where is calcium found? In milk, right? But it's still a metal. Right? Calcium in itself, by itself, is a metal, but we don't see chunks of metal floating around in our milk, right? Calcium in milk is found in a compound, and so our body extracts the nutrients and the different minerals it needs out of those different types of foods. Does that kind of make sense? Right? I think that's probably something that we knew, but it's good for us to hear it one more time. Okay? Any questions with that? Okay. These group 1 elements, lithium, sodium, potassium, they are really, really active, especially with water. Do you know what happens when these metals react with water? They go boom, right? They go boom. Sometimes they fizz if it's a small reaction, but most of the time they explode. And they're so reactive and so explosive that even the water from your hands could cause you to get a burn, right? If you would handle these metals with bare hands, it could cause a burn just from the amount of moisture that's found in your skin and stuff like that. So they're really, really reactive with water. Okay, the reason for their reactivity, and I want to talk about this a little bit more in detail, is that they only have one valence electron. Have you heard the term valence electron before? Yeah. Okay, some of you hasn't. Valence electron. Valence electrons are the outermost electrons in an atom. Okay, so they are electrons in their outer shell. All right, and what that means is that those electrons are available for bonding. They're available to bond with other elements. So let's talk through why is it so reactive to only have one valence electron? That's the question we want to answer now. Why is it so reactive because they only have one? All right, so let's think about this. How many electrons do atoms like to have in their outer shell? Do you know how many they like to have in their outermost shell?
8.
8. They like to have 8. They want their outer shell to be full, and their outer shells can hold 8 electrons. So let's think about this example. I'm going to draw up just a really kind of rudimentary example here for sodium. Sodium is in the 1, 2, 3, the third period. Would we agree with that? Third period. So what that means for its electrons is that if this is an atom of sodium, its first level actually has 2. Its second level has 8 electrons. Its third level, its outermost level, only has 1 electron. So do you see kind of this basic drawing I have here for sodium? That's not really what the atom looks like, but it gives us a good idea of how it works, right? So sodium has 1 valence electron in its outermost shell. But what's true about the shell underneath of that? It has how many?
8.
It has 8. So sodium's goal is to have an outer shell of electrons that is full. So here's its options. Its option is to give away that electron and then be left with just the outer shell right there. Or its option would be to gather in 7 more electrons to fill that shell. So which is easier? To give away 1 or to bring in 7? Give away 1. Okay, so here's what sodium likes to do. It likes to just give away that electron. And so then its outer shell now becomes its second level shell. And it does, like we said, have 8. Does that kind of make sense? That's why it's so reactive. It wants to give away that outer electron to anything and anyone that will take it, right? Any atom that wants an electron, it will give it away, right? And so then it's really, really reactive. All right, so these are called the alkaline earth metals. Okay, group 2. Those include elements like beryllium, magnesium, calcium, strontium, barium, and radium. They have a little bit more of a metallic property than the group 1 metals are. So they're a little bit harder, a little bit tougher. They don't have quite the soft texture like the group 1 metals do, but they're a little bit more metallic like we think. They are slightly less reactive than group 1. Can you guess as to why that might be?
Because there's 2 valence electrons.
Bingo. There's 2 valence electrons in group 2. Okay, they are still too reactive to be found in nature, but they have 2 valence electrons. So is it easier to give away 2 or to gather 6? Give away 2, right? So it's willing to give away those 2 electrons to anything that would want it. Okay? So the 2 valence electrons found here. Now, I want you to start recognizing this is why we labeled the groups 1 through 8. Because group 1, all of those elements have 1 valence electron. Group 2, all of those elements have 2 valence electron. When we move over to group 3, boron, aluminum, gallium, you'll notice all of them have 3 valence electrons. So we labeled the groups to represent that pattern. Okay, does that kind of make sense? So if I asked you how many valence electrons does fluorine have? Locate fluorine on your periodic table. Look at its group number. Tell me how many valence electrons would fluorine have? 7. Good. Now take a guess. Do you think fluorine would be really reactive?
No.
Okay, that's where we get a little bit tricky because it has 7 valence electrons. How many does it need to complete its 8? Only 1, which means it will take the electron from anything. So it is still extremely reactive. The non-reactive elements are the kind of ones found in the middle, right? They've got 3, 4, 5, 6 valence electrons, right? They don't need anything too badly. So those are the less reactive ones.
So
Okay.
1 through 8 are?
What did you say?
1 through 8 are reactive.
They all have different levels of reactivity, right? The group 8 elements, helium, neon, argon, krypton, those ones are not reactive because they already have 8 valence electrons, right? They don't need them. But fluorine only wants one more, so it's pretty reactive. It will take it from anything. Oxygen, sulfur, selenium, they only need 2, so they'll take them. And then you kind of get less reactive as you move inward on the periodic table. All right, the next part of the periodic table is the transition metals. And it says they're group 3 through 12, but we didn't label our group numbers that way. So I maybe want you to just cross that out. I don't want you to think of transition metals with those values right there. The transition metals on the periodic table and the ones in our classroom are this big red group in the middle. This big red section in the middle is the transition metals. All 10 of those groups right in the middle here are considered the transition metals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 10 groups right here in the middle are the transition metals. They are what we think of as very traditional metals. Okay? They have really, really typical metallic properties. All right, we talked about all these metallic properties a little bit earlier, but a lot of these metals found in the transition part are what we consider really typical metals. Okay, we wrote out all of these metallic properties earlier in the chapter. Can you remind me, what does it mean to be a good conductor of heat and electricity? What's it mean to be a conductor? What do you think? It can pass through it. Heat and electricity can pass through it. What about the word ductile? What does that mean? Ductile is a property of a metal, right? It's a characteristic of a metal. So what does it mean to be ductile?
It can be drawn into thin wire.
Into a wire, good. And then what does malleability mean? What does it mean to be malleable?
Flat.
We can put it into a sheet, like a thin sheet of something, okay? Now, the transition metals, they don't follow the typical patterns of valence electrons. That's why we kind of excluded them from our group numbering. They have a variety of valence electrons, okay? A lot of different numbers of valence electrons. They don't follow a typical pattern. So that's why we didn't include them in the way we number them. I want you to look at the transition metals and see, do you recognize some elements in there? In the transition? Nickel, titanium, gold, silver. Yep, platinum, zinc, iron, right? Those are all metals that we think of when we think of metals. Those are the ones we tend to think of, right? They have very typical metallic properties. The only one I think that doesn't sit there that fits in our description or our thoughts of metals is lead and aluminum, right? Those are the only ones and they're sitting kind of close here and here, okay? All right, we're going to skip over now to group 17. We're going to kind of skip those group 3, 4, 5, and 6. They're fine, but they don't do anything really special, okay? Group 17 contains elements like fluorine, chlorine, bromine, iodine, and astatine. They are the most reactive group of non-metals, okay? We made a distinction last class about metals and non-metals. Do you remember? Where are the non-metals on the periodic table? To the right. To the right of, what did I call that line?
Metallics?
No, but what did I call that line that we drew? Do you remember what I called it?
No.
The stair step, right? It looks like a set of stairs, right? So the non-metals on the periodic table are to the left of the stair step. Metals are to the right, and metalloids kind of surround them. So later I'll give you a chance to kind of color in what those things are. But for right now, we're gonna just leave it at that, okay? Halogens can be gas, liquid, or solid at room temperature. Most of them are gases, but bromine is actually a liquid at room temperature. The other, fluorine, chlorine are gas at room temperature, I think. So they have a little bit of a different set there. They are in group 7, okay? I want you to label this here differently. I think with my other class, I labeled them all the way, but I want you to change this to group 7, not 17, okay? Because we labeled our groups 1 through 8, not 1 through 18. So group 7 has 7 valence electrons. That's a really important pattern that I need you to pick up on, okay? Usually these elements are not found alone in nature because they are really reactive. Remember, they only need one electron to get them to where they want to be, but they are not reactive with water. So these are not going to be things that cause problems with water, right? All right, last group that we're going to look at is called the noble gases, and they are group 8. So again, I want you to change that from an 18 to an 8, because that's how we chose to label them. They're group 8. Uh-huh.
So you wanted to change the group 17 to 7?
Yes.
Helium.
Helium, good. Neon too. What do we know about neon? What do we hear of it for? Yeah, it's fluorescent. We use it or we see it often in neon lights, right? That's really a popular concept for us, and we're going to talk about that here in a second, okay? The noble gases are generally unreactive. Can you remind me why they're typically unreactive?
Because they have 8 valence electrons.
They already have all 8 valence electrons that they want, okay? They're gases at room temp. They have full outer shells, and actually almost all of these gases are used in what we call neon lights, right? We call them neon lights, but in reality, neon lights are made up of a mixture of those gases because each one emits a different color of light. And so the mixture of those gases gets us to different colors of neon lights. All right, does that kind of make sense? So they all emit a different color, and then they're going to see that a mixture of those have the color that they want in neon lights. Okay? All right, the last 2 parts of the periodic table are the bottom sections right here called the lanthanides and the actinides. They sit below the periodic table, okay? The lanthanides are shiny and they behave similarly to group 2 metals. The actinides are all radioactive, which means they're dangerous for us to handle, right? Some are found naturally on Earth, but actually most of them are man-made. Did you know that there are some man-made elements? Right? Man-made elements are made in a lab, right? They talk about a different arrangement or configuration of protons, neutrons, electrons, and they're able to stabilize a few elements. Any guess as to how many man-made elements we have?
2.
35 man-made elements. 35 man-made elements. So you might want to write that down just as a separate note. 35 man-made elements. Now, the lanthanides and the actinides are the 2 periods or the 2 rows that sit below the periodic table. Okay, just like on yours, they sit right down here. The only reason they do that is just to save space. If they were going to sit in the periodic table where they're supposed to go, it would look kind of funny and it would take up space. This is what it would look like. Right, here's the green is the lanthanides and the actinides. So it throws off our group numbering. It throws off our valence electron patterns. It just throws some things off. So they leave them where they are currently.